Hello guys, welcome back to my channel. And in this video I would like to do a very interesting Putnam problem. So let's get started. So the problem that we have to work through is simple really. Say we have I, which is defined as integral from 0 to infinity of sum from k equals 0 to infinity of minus 1 to the k times x to the 2k plus 1 divided by 2k double factorial multiplied by sum from m this time equals 0 to infinity of x to the 2m divided by 2m double factorial the whole thing squared dx. So it looks like a lot. It's crazy. Two sums multiplied with each other inside an integral, that to an improper integral from 0 to infinity. So it really helps to write down terms. So say we let integral from 0 to infinity. Let's write down some terms of this series. So when k equals 0, we have x to the 1, which is x, divided by 0 double factorial is 1. So just x over 1 or x. Then minus, it's an alternating series. When x is 1, we have 2 plus 1, 3 over we'll have a 2 times 1 or 2 double factorial, and a double factorial is defined in this way. A double factorial is equal to a minus 2 times a minus 4. You start with a minus 2, a minus 4 until you reach 1. So it's basically factorial was having consecutive terms being multiplied. Double factorial is basically jumps of 2. So a, then a minus 2, then minus 2 of that, and a minus 4 until 1. In our case, 2 double factorial is just 2. Next term is x to the 5th divided by 4 double factorial. According to this formula, that will be 4 times 4 minus 2, which is 2. So 4 times 2 or 2 times 4. Because after 2 we just have like that's like the last term. After that we have like a 0 minus x to the 7 divided by 6 double factorial, which is 2 times 4 times 6. And the other sequence, the other series is 1 plus x squared over 2 squared plus x to the 4th over 2 to the 4th 4 2 to the 2 squared 4 squared plus x to the 6 divided by 2 squared 4 squared 6 squared, and that goes on dx. So we have this crazy integral right here, and we need to evaluate this. So what I'm going to do is I'm going to look at the less crazy version, without the square in the denominator. I'm going to look at this series first. I'm going to call it S. So S is x minus x cubed over 2 plus x to the 5th over 2 times 4 minus x to the 7th over 2 times 4 times 6. And that goes on, which has a general form like we had in the start. Sum from k equals 0 to infinity of minus 1 to the k times x to the 2k plus 1 power divided by 2k double factorial. Now one thing worth noting is that this can be written as x minus x cubed over 2 times 1, which you can write as 1 factorial, plus x to the 5th divided by, now let's just factorize 2 from the first term and the second term, giving us factor of 2 and multiplied with a factor of 2. So 2 squared times 1 into 2, which can be represented as 2 factorial, minus x to the 7 divided by, now we are pulling out 3 2's, so 2 cubed times 3 into 2 into 1 after factorizing will give us 3 factorial. So now our generalization becomes sum from k equals 0 to infinity of minus 1 to the k times x to the 2k plus 1 divided by 2 to the k times k factorial. So this significantly reduced the difficulty of this series S. Now noticing the factorials we have here, this might remind you of some Taylor series. Well, to be precise, three Taylor series. Those were the sine of x, and I'm going to write that out, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and that goes on till infinity. Second was the cosine series of 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and basically that goes on. And the last, e to the x, which was basically, this was very simply 1 plus x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and that goes on. But the thing is, notice the original expression. We weren't skipping any terms, right? Any factorial terms. So, like in the sine, we were skipping even factorials. So we are skipping even factorials. So we are skipping 4 factorial, 6 factorial, 8 factorial, so on. Even 2 factorial for that matter. And here for the cosine, we are skipping odd factorials. And that's not favorable, because if you look back to your original S with 1 factorial, 2 factorial, 3 factorial, so we have to include both even and odd, and inclusion of both even and odd is in this e to the x series. So here we are including even plus odd factorials, and we can write the general form of this easily. We have the sum from n equals 0 to infinity of x to the n divided by n factorial. Simply that. But we have this factor of 2, 2 squared, 2 cubed, and also the power of x. We start with x cubed, x to the 5th. So power of x is alternating, so as to, like skipping 2's. So it was x to the 1, then add 2 to that x cubed, add 2 to that x to the 5. So every time successive terms have basically 2 added in the power of x. And the way to do this is to first tweak the argument x to be x squared. So we have 1 plus x squared over 1 factorial plus x squared squared, right? So x to the 4th over 2 factorial plus x squared cubed is x to the 6th over 3 factorial. So now we've at least maintained that skipping of 2. So if you notice, 2 plus 2 is 4, 4 plus 2 is 6. So adding 2 to the power of x, we're basically increasing by 2 each successive term, just like this. But here we had odd powers, we have even powers. We can rectify that in the end. But notice one great flaw is we have an alternating series here. We don't have that here. So why not take e to the minus x squared? So this will make all the alternating terms go to 0. So to basically build this up, what we can do is we can take e to the minus x, which will be 1 minus, for all powers of x, we have a negative x over 1 factorial plus x squared over 2 factorial minus x cubed over 3 factorial, with a general representation of sum from n equals 0 to infinity of minus 1 to the n times x to the n over n factorial. And now on this we do the tweaking of parameters. For x we take x squared. So with that we have 1 minus x squared over 1 factorial plus x squared squared or x to the 4th over 2 factorial minus x to the 6th over 3 factorial with a general representation of sum from n equals 0 to infinity of minus 1 to the n times x to the 2n over n factorial. But notice we still have to deal with this these powers of 2 in the denominator. So for that, instead of having just an e raised to minus x squared, why don't we take e raised to minus x squared over 2 in the argument? So when we do that, plugging this in place of x for this series, we have 1 minus x over 2 over 1 factorial plus x over 2 the whole thing squared over 2 factorial minus x over 2 the whole thing cubed over 3 factorial, and that goes on, which we can simplify to 1 minus x over 2 times 1 factorial plus x squared over 2 squared times 2 factorial minus x cubed over 2 cubed times 3 factorial. It's actually, well, x squared here, x squared here, x squared here. So this will be 4 x square square. X square cube will be 6. My bad for that. Okay, so we have maintained now the denominator. We have the perfect denominator. It's just that initially, we have odd powers of x. Here we have even powers of x. We start with x. Here we start with x, with 1 here. So to rectify that, but before doing that, let me just write the general representation of this. This will be minus 1 to the n times x to the 2n over 2 to the n times n factorial. Now to rectify this, why don't we multiply by x square, x on both sides? So x times e to the minus x squared over 2 will be x minus, this is x squared, my bad, x cubed, x squared times x is x cubed over 2 times 1 factorial plus x to the 5th over 2 squared times 2 factorial minus x to the 7th over 2 cubed times 3 factorial, and that has a general representation of sum from n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 divided by 2 to the n times n factorial, and that's precisely this. We just have different indices for summation, but that's essentially the same. So we have successfully established that our first sum is basically equal to x times e raised to minus x squared over 2. Isn't that a fascinating and a wonderful fact? That was with regards to s. Let's look at this s naught. So s naught is basically 1 plus x squared over 2 squared plus x to the 4th over 2 squared 4 squared plus x to the 6th over 2 squared 4 squared 6 squared, and that goes on till infinity. But the sad part is, even if you look at the general representation of this, sum from m equals 0 to infinity of x to the 2m divided by 2m double factorial, the whole thing squared. And even if you look at basically the general representation of this, which, using the formula for the double factorial, we have x to the 2m. We basically use this trick of pulling out 2 for even, that works for even double factorial. So we have 2 to the m times m factorial, but everything is still squared. But the sad part is there is no Taylor series that we can use that involves square of a factorial. I mean, we had seeing regular factorials. We did that with three series that had factorials in denominator: sine x, cosine x, and e to the x. But there is no series, Taylor series, you can check it, which involves the square of a factorial. So what we're going to do is we are going to just let this be as it is. We're going to represent this with a general form, and we are going to just take this integral and plug everything back in on a fresh page. See you there. So that's the basic original problem we started with, but we know the value of this, right? This is just x times e to the minus x squared over 2 multiplied with this, basically sum from m equals 0 to infinity of x to the 2m divided by, we can represent this double factorial as 2 to the m times m factorial, but the whole thing squared because of the square, dx. So that is basically the integral, the simplified integral that we need to calculate. And at this point, what I really want to do is I want to assume convergence, assume uniform convergence, and in Putnam questions like this assumption is mostly valid most of the times. So that enables me to interchange this integral and this infinite sum. So I have I is equal to sum from m equals 0 to infinity of, we'll take all the m terms outside, 1 over 2 to the m times m factorial squared, and integral from 0 to infinity of e to the minus x squared over 2, and then this x to the 2m multiplied with x will give us x to the 2m plus 1 dx. Now it would seem pretty evident or reasonable to use this substitution. Let y is equal to x squared over 2 such that dy is 2x over 2 dx, or simply x dx. So this means x is just square root of 2y. So we have square root of 2y dx, that's equal to basically dy. Upper and lower bounds remarkably remain unchanged. So we have sum from m equals 0 to infinity of 1 over 2 to the m times m factorial squared, integral from 0 to infinity unchanged, e to the minus y, x is square root of 2y but raised to the 2m plus 1 power, and then dx is dy over square root of 2y. Now one great thing is one of this and one of this will cancel out. I is basically sum from m equals 0 to infinity of 1 over 2 to the m times m factorial squared times integral from 0 to infinity e to the minus y. We have square root of 2y to the 2m power, which can basically be written as square root of 2y squared, the whole thing to the m power. So the root and the square go off. We have 2y to the m power dy. Now take the 2 to the m outside, it does not depend on y. We have sum from m equals 0 to infinity of 1 over 2 to the m times m factorial all squared, and we have a 2 to the m on top, integral from 0 to infinity of e to the minus y times y to the m dy. And what is this? Gamma of m plus 1, right? So we have sum from m equals 0 to infinity of 1 2 to the m will cancel off nicely with one of this, so we just have 1 over 1 2 to the m, and we still have the m factorial squared. This is gamma of m plus 1, as I suggested. That was the entire purpose of using this y substitution, because we had an integrand that almost resembled the gamma function interior. Now, for all our purposes, for all our m, because m is an integer, m is basically a positive integer, including 0. So for all these purposes, gamma can be written, gamma of m plus 1 can be written as m factorial. So if we use that, we have sum from m equals 0 to infinity of 1 over 2 to the m times m factorial squared and m factorial. So one of these will again cancel off. We've sum from m equals 0 to infinity of 1 over 2 to the m times m factorial, just 1 m factorial now. This can be represented as sum from m equals 0 to infinity of half to the m divided by m factorial. And what does this look like exactly? I mean, does this remind us of any series? Remember that e to the x was defined as sum from k equals 0 to infinity of x to the k over k factorial. We just have m replaced by k, and in place of x we have half. So all of this will just be e to the half power, or simply square root of e. So I is entirely, the monster expression is entirely equal to square root of e. Isn't that a really, really nice result? And so to conclude, we had basically this crazy expression that we had to evaluate. Then we wrote some terms of the series to get an idea of what was going on. And all of this, we simplified the first series using Taylor series. We tweaked the Taylor series of the exponential function to fit this structure, and we just wrote the second series in its general form. Use substitution, interchange the sum and the integral. Observe that one of the entire integral was going to gamma in a sum, and then we cancel off some excess terms, and then we ended up with a Taylor series that looked like, say, this sum from m equals 0 to infinity of half to the m over m factorial, which we quickly recognized to be e to the half, the Taylor series of e to the half, which is just square root of e. And that's a really, really nice result, as is expected of Putnam problems. They have these excellent, beautiful results. So that's it for this video. I hope you could learn something and enjoy yourself. So please like, share and subscribe to my channel, guys. So if I get like 100 subscribers, I'll be able to make like a question and answer with you guys. So I want to reach that goal as soon as possible. And in the meantime, stay home, stay safe, and peace out. Recommend me to your friends, mathophiles. Don't forget to do that. That's more important. Anyways, peace out.